Get started. Well, hello everyone, welcome back. So before we begin, I managed to upload the recordings of the last 2 weeks in the course schedule just yesterday night. But if you missed the first class, I think a bunch of you missed your first class because of the visa reasons or starting late. Like, say, if you missed your first class or the second class, you can go back and watch the recording. Okay. Um, at this point, everyone should have access to Piazza and Gradescope. Is there anyone in the class who still doesn't have access to Piazza and Gradescope? Also, I see that in Piazza, 30 of you have not activated your account, which means you have not opened Piazza at all. Okay, so again, is there anyone in the class right now who hasn't opened your Piazza? Well, there are 30, so there should be at least few here. Okay, some of you. So you should go open your Piazza. So the invitation went to your Poly email ID. Okay, so Piazza is where you can ask all your questions, and all the announcements happen through Piazza as well. Well, I make sure to send an email whenever there's an announcement there, so that it at least comes to your Poly inbox. But in general, try to sign up and use Piazza. Okay. And what about Gradescope? Is there anyone in the class who hasn't been able to access Gradescope? Everyone is in Gradescope, and everyone knows that assignment 0 is due tomorrow. Is it today? 10th, yeah. So it is today. So everyone knows that it is due today to 10 p.m., right? A0 is not graded, but if you don't submit your A0, the rest of the assignments will not be evaluated. Okay, so it's mainly for the honor code. So even if you cannot finish all the questions, do a few questions, like do a couple of questions, sign the honor code, learn how to tag questions in Gradescope and submit it tonight. Okay, so I don't think everyone has submitted to Gradescope. I can quickly check. So 74 students have submitted to Gradescope, and we have 128 students in the class. So approximately 50 students have not submitted their A0. So please try to do it after the class so that your future assignments would be graded. Is that clear? And assignment 1 was released last week. So today we will cover everything that is needed to finish your assignment 1. But however, you had enough things to get started with last week itself, right? Like so tomorrow's lab session is going to be a recitation on linear regression, followed by office hours for the assignment. Okay, so Hardy is going to do it. So he'll do, I think, 1 hour recitation followed by the rest of the time for assignment 1 office hours. Is that clear? Okay, so let's get started. So what did we do last week? Yeah. Yeah. Linear regression, right? Like, so it's like we started with a simple linear model and came up with a least square objective, right? Like, and we tried minimizing it by differentiating it, setting it to 0. And we arrived at a closed form solution for linear regression. And we also discussed the idea of overfitting. So can someone explain what is overfitting? Yeah. Okay, so maybe, yeah. Oh, maybe can someone explain overfitting? Let's see. I click here. Okay, so let's see if this is better. Yeah. So your model is overfitted on the training data. So what are the implications of that? So it will do poorly when it comes to generalization. Okay. You had something else to add or the same? Okay. And how can we address this overfitting issue? Like, so we looked at a few solutions, right? So what can someone else, like, so maybe, yeah?
Add more data.
Adding more data help. Okay. So what are the solutions? Yeah. Okay, this is in the context of polynomial regression. Like you can just reduce the degree of the polynomial if you think it is too complex polynomial to begin with. Yes. What other solution? Yeah. Regularization. Regularization. So what is regularization? So when you add terms, so we can penalize very high weights. Okay. So we found that one of the reasons for overfitting is weights growing too much. So regularization is this idea of adding a penalty for growing weights. Like so, like if you put a L2 regularization, then you're trying to minimize the L2 norm of the weights, right? Like so, which means you would prefer smaller weight solutions, which would not overfit that much. Okay, so anything else? Okay, so that is good. And towards the end, we also discussed the idea of, yeah. Okay, so we will talk about that more today. So what I mean by closed form solution is you can implement the solution in one shot. Like, so it's not iterative. It's not iterative. Like, so you don't need to do a lot of iterative computations. Okay, so it's like a single equation that you could implement easily. Okay, so in the case of linear regression, like because the model is linear and the objective is quadratic, right? So it was easy for us to differentiate it, set it to 0, and come up with an equation for W, which you can easily implement, right? So soon we will see models where like you cannot differentiate, set it to 0, and come up with a closed form equation anymore. So then we need to resort for iterative approaches, which is what I think we will focus today. Is that clear? Okay. And towards the end, we also looked at the idea of basis functions, nonlinear basis functions, right? Like, so I want to start from there. Like, so typically, when you have a linear model, like W0 plus W1x, for example, right? So this model takes X as input and makes some prediction Y. So because it is linear, it can only fit a line, right? So this kind of model can only fit a line, but the direction, the angle and the position of the line, you have the flexibility through W0 and W1, but you can only fit a line, right? For a lot of real life regression problems, like just fitting a line is not enough. So we need more complex functions, like and we looked at polynomial regression as one example, but in general, the idea is you can take X and construct some nonlinear basis functions, phi. Okay, so then you use a linear model. Right? Now, depending on what kind of nonlinear basis function you're using, you're going to get more complex curves. So if you're using polynomial, right? Like, so then you're going to get, depending on what degree of the polynomial, it's some curve which looks like this, right? So we also looked at various other basis functions like Gaussian basis function or exponential basis function, or like you can use sine, cosine functions, right? Like, so you can use any sort of these nonlinear basis functions, put a bunch of them together, you're going to model a complex curve. Okay. The benefit of this approach is this part is fixed, right? Like so we are handpicking like a type of nonlinear function. So once you pick that, this is still linear, like the model is still linear, which means the closed form solution that we learned still applies here, right? Like so typically the solution here is W star is phi transpose phi inverse phi transpose Y, right? So that still holds. Is that clear? Okay, so Before I move on to something fresh, like, so I want to talk about some geometrical intuition for what least square is doing. Okay, so we're going to look at the geometry of these squares. Okay, so first let's try to understand that from pictures, right? Like, so let's say I have a bunch of data points like this. Okay, so when I try to fit a line using least squares, like what I'm doing is like I'm trying different lines, and those lines are going to have some error, right? The error is captured by least square. So for example, let's say I draw a line like this. Okay, so this line is going to have some error for each data point. Like, so for this data point, the error is so small, right? For this data point, the error is almost zero, right? Like, so for the third data point, this data point has a huge error. This data point has this much error, right? So what least square does is it basically takes all these errors, it squares them and sums them together. Okay. So that is the least square error, right? Now I can draw another line. So let's say I have a line like this. Maybe I'll try to draw the ideal line. Okay, let's say I have a line like this. So for this line, the least square error is going to be the squares of this error, this error, this error, this error. Right? So in general, there are many lines that are possible. Like, so we are going to search for a line which has the least error in terms of the square error function that we have. Is that clear? So intuitively, this is what is happening, right? So we are searching for a line, right? Like, so I think I mentioned that I should have an animation last week. Let's say we are searching for a line. So the line just moves around, okay? And you will stop when you find a line which has the minimum least square error, right? So what does this mean mathematically, right? Like, so to understand this, like, we're going to take a really simple setup. So I'm going to consider just 3 examples and 2 features. Okay, so the features are phi1 and phi2. So we have only 3 examples and 2 features. So the prediction y hat is given by w1 phi1 plus w2 phi2. Okay, I'm not using the bias here. Okay, so that it's easy for us to see what is happening. So, but whatever I'm saying is true even when you have the bias. Okay. Okay. So when I have 2 features, and this is my model, y hat is a linear combination of phi1 and phi2. Is that correct? So if these phi1 and phi2 are vectors, then y hat essentially spans the subspace covering the 2D. It's basically it's going to lie in the span of these 2 vectors. Is that correct? So we have 3 examples, right? Like, so I'm going to construct phi1 vector and phi2 vector. Phi1 vector is basically a 3-dimensional vector, like where each row is the example, like basically each entry is the feature of that particular example. There are 3 examples, right? So this is a 3D vector. This is also a 3D vector. Okay. So let's say I am in a, okay, maybe it's going to be hard for me. I'm going to do a 3D picture in 2D iPad. So let's say This is my phi 1 and this is my phi 2. Okay. These are phi 1 and phi 2, and y is going to be somewhere in the span of this 2D plane of phi 1 and phi 2, right? Like, so let's say the plane for this looks something like this, and the actual, well, maybe let's first do the y hat. So the y hat is somewhere here. So depending on the value of W1 and W2, the y hat is going to be somewhere here, right? So this is the limitation of the linear model. Because I have a linear model, I can only do linear combination of the features. But in reality, the data might be in such a way that the output is not a linear combination of features. Okay, so it could be something else, in which case my real y could be outside this plane. Okay, so the real y is outside this 2D plane. Now, if I want to somehow find the line which has the least square error with respect to this y, what would that y hat be? Yeah, projection. It's just a projection, right? Like, so it's going to be the orthogonal projection of this y to this subspace. Okay, so it's going to be, so this, I'm gonna erase this one. Okay, so this is the best y hat that you could find. Is that clear? So maybe I'll try to redraw this in a better way. So if I have a surface that is spanned by phi 1 and phi 2, and my y is somewhere totally outside the surface, right? Then the y hat that you could get, the best y hat that you could get, is just the closest projection of y in the subspace. Okay? So this is what linear regression is trying to do. This also shows the limitation of linear regression. Like, so the linear, like, as you can clearly see, it only spans this place, right? Like in the entire 3D space that we have, it spans just a plane. Why? Because it is just a linear combination of features. Is that clear? Any questions? Okay. So this is useful to know, but let's move on. Now, there was a question about what do I mean by closed form solution, right? Like, so in the case of linear regression, when I have y hat is equal to W transpose X, right? And with the error function that we had, we were able to differentiate it, set it to 0, and get, or maybe let me also write the error function again. Like, so the error function that we had was W transpose X minus Y transpose Y transpose I. I think we need the N here. Right? So maybe I'm not putting the transposes in the right place, but you get the idea. So this, like, you have a simple linear model and you have a least square error function, right? So in this case, Because my model was linear and the objective function was just a quadratic objective function in terms of the parameters, right? We were able to get a closed form solution, which was basically x transpose x inverse x transpose y. Right? Now, this might not be possible for every model that we are going to develop, okay? So if you remember, even for L2 regularization, we were able to do closed form solution, right? There was a reason why I started with L2 regularization instead of L1 regularization. Like, so just like how we added a penalty on L2 norm of the weights, we could also add penalty on L1 norm of the weight, right? But then you cannot get closed form solution. So you can get closed form solutions only for certain special classes of functions, okay? So what can we do when we cannot get closed form solution? So I have a function I want to minimize, but it is so complex that I cannot differentiate it, set it to 0, and get a closed form solution. So what can we do? Yeah. Okay, so, well, okay, we can differentiate this function, by the way. So it's not the question of differentiability. Like, so it is just that the function might be complex, that when you differentiate and set it to 0, you don't get the closed form solution, right? Also, moving forward, like, we're going to see more and more complex functions, okay? So like it's going to be like a lot of work to differentiate them, set it to 0, and try to find closed form solutions, okay? Now, there is actually a more scalable approach, which is an alternative for whatever we learned last week, okay? So which is the idea of gradient descent. Okay. Now, gradient descent is an iterative algorithm to compute the minimum of any differentiable function. Okay. So if you have a function that is differentiable, it is just that it's not possible to get a closed form solution, then it is going to be easier to find the minimum by using this iterative algorithm. Is that clear? So let's see how to do that, right? Like, so we're going to go back to the linear regression problem. So I have some input. Just for simplicity, let's assume that x is just one dimension, y is one dimension, okay? So I have an input which is one dimension and y which is also a single dimension. And I have a really simple linear model, okay, which is y hat of x given w is equal to w0 plus w1x, okay? And the parameters of this model are w0, w1, right? And the loss function or error function that we are going to use is going to be 1 over 2n summation I is equal to 1 to capital N y hat of xi given w minus yi the whole square. And our goal here is to minimize the loss function with respect to w0 and w1. Is that clear? So I'm just rewriting the linear regression problem. Okay, so but this time instead of differentiating this and setting it to 0, we are going to take an alternate approach for solving this problem. Okay, so this is what we are going to do. Because this is just two parameters, right? I can easily visualize this last function. So the last function takes W0 and W1 and computes the error with respect to the training set, right? So you can pick a random W0 and W1, you're going to get some loss. Now you can do this for all possible combinations of W0 and W1. Well, of course, W0 and W1 has infinite range, but you pick a reasonable range and try every possible combinations in the grid, you're going to get some loss, right? So let's look at how that function looks like. Okay, so here you see for different values of W0 and W1, okay, I pick, for example, let's say we pick this point, right? Like, so which is basically W0 is 0 and W1 is minus 20 approximately, okay? So that is going to have this loss, okay? So for every W0, W1 that you can pick, you get some loss, and I'm just plotting all those losses here, okay? So this is basically a visualization of my loss function. So when I say minimize the loss, what it really means is to find the minimum of this function, right? So we want to find a combination of W0 and W1, which has the least error function. So here is a simple iterative approach, okay? Imagine that someone puts you here randomly, okay, and you're blindfolded. Your task is to reach the minimum of this function. So what would your strategy be? Someone else. Yeah? Try to feel. Yeah, try to feel where the steep is and move towards that, right? Like so basically you're blindfolded, like so you're going to check all around, right? Like so you're going to check with your leg and find where the steepest point is and take one step towards that and just continue this process. This is a good heuristic, right? Like so basically you start here. So let me clean this up. So let's say you start here, okay? You're going to find where the steepest point is. You're going to take a step towards that. Now you're here. Again, you're going to repeat the process. You're going to find, oh, sorry. You're going to find the steepest point. You reach here. You continue this process, right? Eventually you will reach a place where when you try taking a step, all the 360 degrees, your steps are going up, right? Like you search all over, like every direction you try to take a step, it's going up. So what does that mean? You reached a minimum, right? Like so this means that you reached a minimum. Like so you are at a minimum because in all the directions things are just going up, like not down, right? So then you stop. Is it clear? It's a really simple algorithm, right? Like so now we can formalize it a little bit, okay? So instead of you being blindfolded, last function, right? Like what we are going to do is like we're going to randomly pick a W0, W1. Okay, so let me erase this once again. So I'm going to pick a random W0 and W1. So what does this mean? This random W0, W1 is going to put me somewhere in this loss function, right? Well, if you're extremely lucky, you're going to pick a random W0, W1, which puts you very close to the minimum, right? So that rarely happens. So we pick something random, and that puts us somewhere here, right? Now, how can I find which is the steep of, which direction is the steep of this function? Yeah, the gradient gives this information, okay? So if you compute the gradient of the function, okay, it's going to tell you, the gradient of this function is going to tell you the steepest ascent direction. Okay, the gradient always points you to the steepest ascent direction. Now we want to do a descent, right? Like we actually want to find the minimum. So the simple trick here is like, so you compute the gradient, just go in the opposite direction. Okay. So however, we don't want to take big steps. Okay. So like, I'll tell you the problem with taking big steps soon. Like, so we want to take conservative steps. Like what I'm going to do is I'm going to find the opposite direction of the gradient and take a tiny step in the direction, then continue this process until I reach a point where the gradient is 0. Mathematically, when the gradient is 0, it means you're in a local minima or maxima. Okay? Is that clear? Okay, so now how would this look like? So this is going to look something like this. Like, so my W0 is equal to W0 minus alpha times dou L by dou W0. W1 is equal to W1 minus alpha times dou L by dou W1. Okay, now this term is my gradient. The gradient of, this is basically the derivative of the last function with respect to W0. So that is the gradient, okay? So this is a gradient. And the alpha that you see here, right? Sorry. This is called step size or learning rate. So typically we will set alpha to be 0.01 or 0.001 or 0.0001, like a very small value. Okay. So as you can imagine, alpha is a hyperparameter. Okay, so we will pick an alpha before we begin this process, and that is a hyperparameter. So once you fix the alpha, let's say to 0.01, the gradient descent works like this. Like, so you will randomly initialize W0, W1. Okay, so maybe let me write down the algorithm explicitly. So here, this is how the algorithm looks like. So first I'm going to randomly initialize W0 and W1. Okay, so you will be implementing gradient descent in your first assignment. So you're randomly initializing W0 and W1. So then I'm going to repeat until convergence. Okay, W0 is equal to W0 minus alpha times dou L by dou W0. And W1 is equal to W1 minus alpha times dou L by. Is that clear? So I'll keep doing this until convergence. Like, so when will the convergence happen? Like, so when will this update converge? So what is the condition for this update to converge? Yeah. When the gradient is 0. When the gradient is 0, the second term becomes 0. So W0 is equal to W0 and W1 is equal to W1, right? So until the gradient becomes 0, I'm going to continue this process, which means I start somewhere randomly and just keep moving until I reach the minimum. Is that clear? Now, this algorithm only guarantees that you will reach the closest minimum, right? It doesn't give any guarantee about whether this is the best possible minimum. that you could reach. Okay. However, we know that in the case of linear regression, because it is a quadratic function, right? So this is a special case of convex function. So what are convex functions? Like convex functions have a global minima, and that is the only minima that it has. It has a unique global minima. Okay? So there is no local minima in convex function. Okay. So which means if you do gradient descent in a convex function and the gradient descent converges, it has to be the global minimum, right? So that's the nice thing about convex functions. Like, so with convex functions, if I start at some point randomly and do gradient descent, right? The gradient descent is going to take me to the global minimum. Is that clear? However, let's say I have a function that is not convex. I have a function like this, and I want to find the minimum of this function. Okay, I'm trying to minimize this function. So now there are two minimas here, right? Like, so there's a global minimum here, right? There's also a local minimum here. Now, let's say I start somewhere here, and I'm doing gradient descent. So can I reach the global minimum? Yeah. It depends on the learning rate. Let's say I have a small enough like I have a very small learning rate. I have a very small learning rate, and I'm starting here. I'm doing gradient descent. Yes. Yeah, I'm saying that I'm initializing here. Yeah. It cannot, right? Like, so the gradient descent cannot reach the global minimum because I'm starting here and I have a very small learning rate. It's just going to move like this, right? It's going to move like this, and it's going to reach this point. The gradient will become 0 because it's a local minimum. Gradient descent cannot move after this. So it's stuck there. Okay, it converged, but it converged to a local minimum. However, well, like as you said, like if I was lucky and I initialize here, right? So then, yes, this version is going to converge the global minimum, right? It really depends on the initialization and, as you rightly said, also the learning rate. Okay, so why is it dependent on the learning rate? So let's see what happens when I try different learning rate, right? Like, so there is a reason why we set very small learning rates. Okay, so if your learning rate alpha, right? Like, so if alpha is too large, okay, so what could happen is, well, maybe let's start with the case when alpha is too small. I'm going to go to the next page. Let's start with convex functions first. Okay, so I have a convex function. I'm starting here. If alpha is too small, okay, so what could happen is gradient descent can be very slow. Okay, so you're starting here, you're taking tiny steps. Okay, it's going to take you a long time to reach minimum because your steps are too small. Let's say you're putting 0.0001. Okay, now what would happen if alpha is too large, right? So again, I'm going to do this with convex. We'll move to the non-convex case soon. So if alpha is too large, let's say I do a learning rate of 2, step size 2. Instead of 0.01, I'm doing step size 2. It's too huge, okay? So people don't do this. So if you have a very high learning rate, so what could happen is you're starting here, right? You're going to make a big jump to here. Looks like we are doing faster, right? Like, so it seems to be a good idea to have larger learning rate, right? So now the next step, we're going to make another big jump. Okay. So the next jump that you're going to make, because your step size is too big and it is actually bigger than this remaining distance, right? So your next jump is going to put you somewhere here. Okay. Now you want to correct it. You want to go back, right? So because your step size are larger, like what could happen is every correction that you're trying to make would make things worse and you would completely diverge instead of converging. Is that clear? So if your step size is too large, right? Like so then gradient descent can actually diverge. Okay. So now let's go back to the non-convex case, right? Like so here, let's say you're somewhere here. If your step size was large, sometimes there's a chance that you go here. Okay. But this is not a good excuse to have larger step sizes because once you go here again, you're going to diverge the next step, right? Like so if your step size is large, there is a chance that you would skip the local minimum, which is sometimes nice in non-convex cases, but you have to be careful because in general, larger step sizes lead to divergence. So the typical step sizes that you would see people using are something like 0.001 or 0.00001. Like it's always 1 e power -3, -4, -5, -6 kind of step sizes. Is that clear? Now, one thing I want to highlight is this step size or learning rate, whatever way you call it, is probably one of the most important hyperparameters in machine learning. Okay, so every machine learning algorithm that we are going to look at this, look at in the future classes, we are going to use gradient descent to minimize the function. Okay, and the step size plays an important role in all these algorithms. Okay, so like tuning the step size is really difficult. Like so, you need to be careful in how you tune your step size. Like, so that's going to give you good or bad results. Is that clear? Any questions? Yeah.
The test that that relates to life. Is there a possibility that we don't find the the minimal the minimal
In which case?
when the learning rate is too large?
Yeah. When the learning rate is too large, like you would diverge sometime, like most often. So then you are not finding the minimum, right? Yeah. Yes, you can do all those things. Like so, like if you want to be okay, so that's a nice heuristic. Okay, so like when you are starting somewhere here, right? You don't need to be too careful. In the beginning, you can afford to take larger step sizes, right? Like which means like so your heuristic of varying the step sizes, like sometimes having bigger step sizes, sometimes having smaller step sizes, is a good idea. Okay. There are a lot of algorithms which tries to vary step sizes. Okay, so but at least for the first few weeks, we are going to stick with the basic version of gradient descent, where the step size is a hyperparameter that is fixed before you begin the training. Okay, maybe in few weeks, like so, we will revisit gradient descent again and see how to improve it. Okay, so we will see more optimization, like spread all across the course, even though this is not a course on optimization. Okay, um, so if you remember, probability and linear algebra are prerequisites, but optimization is not. So we're going to do a little bit of optimization, how to minimize functions effectively, like throughout the course. Okay, so I just want to write the I just want to write the gradients for linear regression, and then we'll take a break. So for linear regression, the loss function is 1 over 2n summation I is equal to 1 to capital N W0 plus W1 x I minus y of I the whole square, right? So if I want to implement this gradient descent algorithm for linear regression, then all I need to compute are these two things, right? So we're going to compute these two things for linear regression. So what is dou L by dou W0? So first you would differentiate the outside, right? Like, so it's x squared, when you differentiate, it becomes 2x. So this becomes 2 by 2n summation I is equal to 1 to capital N W0 plus W1 xi minus yi. Then you differentiate internally. You're differentiating this with respect to W0. So you would just get 1, right? This is the gradient of L with respect to W0. Okay. Similarly, you can do dou L by dou W1. This is going to be, so 2 cancels. This is going to be 2 by 2n summation I is equal to 1 to capital N W0 plus W1 xi minus yi times. So what would be the gradient of this term, like the differentiation of this term with respect to W1? Yeah, just xi. So it's going to be xi. These two cancel, right? So now you can just plug it to the gradient descent algorithm that we had and run it until convergence. You can find the solution for least square without doing x transpose x inverse x transpose y. Okay, so sometimes this is actually preferable than doing the original closed form solution, especially if you have a very large data set. The doing x transpose x inverse is costly, right? Or sometimes the matrix is just not invertible. So then it's going to be a problem to do closed form solution. But this gradient descent solution always works. Like, so, like, it doesn't matter whether you have small data or big data. It doesn't matter whether the matrix is invertible or not. Computing the gradient is easy, and you can always run this iterative algorithm. You're going to converge to the minimum. Is that clear? Yeah. For the photo, they have the code windows and metric for there is no solution for that. So the question is like, so is there any solution for the fact that we can only get local minimum, not global minimum, right? Like, so in fact, I don't think there is any known optimization algorithm which guarantees that you can reach global minimum. Okay, so most of the algorithms will guarantee only convergence to local. And for the but let's worry about that later, because right now we don't have the problem of local minimum, right? Like, we're just doing linear regression. So with linear regression, there's no local minimum. So we don't need to worry about it right now, but we will revisit this question later when we have to worry about local minimums. Any other questions? Okay, so let's take a 10-minute break.